Okay, folks, so we're a minute past the hour, so I think we may as well get started. Welcome, everybody. My name is John Perkins, and thanks for tuning in to the USGS Landslide Hazard Seminar's third and final presentation on our mini-series of the landslide response to Hurricane Helene. This meeting's hosted by the Landslide Hazards Program and co-organized with Shelby Arendt and Jamie Kostelnik. And for those of you who are new to this meeting, you can submit questions via the chat window or use the raise your hand feature along with the microphone and video camera. And we'll wait to the end of the presentation to take questions today. And in the meantime, please do your best to make sure the microphone is muted when you aren't intending to speak. So with that, it is my pleasure to introduce Philip Prince, who is a geologist at Appalachian Landslide Consultants, working alongside Jen Bauer, who presented in our last talk. Phil got a BS in Earth and Environmental Science from Furman University in 2004, and then worked in environmental consulting before completing his PhD at Virginia Tech in 2011. He continued to teach there until 2016, and then spent 3 years doing bedrock mapping with the Virginia Division of Geology and Mineral Resources, before joining Appalachian Landslide Consultants in 2019, where he's been ever since. And with that, Phil, I will let you take it away.
Okay, thank you very much. For folks that might have been on the meeting early, I was telling the organizers here that I've tried to pivot my content a little bit based on what Jen Bauer presented a couple weeks ago, because there was exceptional interest in the concept of what we call blowout landslides, which are a liquefying landslide, a flow slide, if you will, that are pretty common in LiDAR throughout the Appalachians. We saw several of them occur during Helene, and their distinction from a debris flow is that they don't erode the slope below them. And you're looking at one right there to start off with. That's me standing in it for some sense of scale. Pretty typical of this type of failure. And as we go here through the talk, I'll try to elaborate a little bit on the terminology and why we use that. It is out of the literature, and essentially we're trying to continue a legacy of describing this type of feature in association with extreme precipitation events. One you see here is pretty typical of this type of failure, and the after effect that you see, which is effectively sort of a scoop or a little divot, if you will, in the hillside. That's quite representative. And the one you're looking at here is actually the one that produced what was sort of a viral video during Helene. In fact, in the top right of that image, you're seeing it, you see September 27th, 2024. This was the Sugar Grove landslide. If you go on YouTube and look up Sugar Grove landslide, you'll see a video of this failure. And folks happened to be looking up slope when it happened. Underneath the leafed tree there, you can see some slide blocks still intact. At this point, it's really spreading and liquefying. The big dark thing below the tree, I think, is actually a root ball of a tree that is riding down slope with the material. And then it almost explosively liquefied and sent a huge wave of mud and colluvium clasts down on the house below. That's the view looking down the slope, and you can see that below sort of the lower edge of the failed area there, the slope is certainly not scoured. It's effectively intact, and it actually has a little bit of deposition on it. The video was filmed from the structure on the right that is behind the tree in the foreground, and the house down there that's being repaired, renovated, under construction was about twice as wide before this failure. Really incredible to capture this happening. And in terms of trying to put it into context, if you know me, I like visuals and sort of conceptual sketches. Contrasting this type of movement with a debris flow, it really comes down to what happens downslope of the failure. So we got our sort of block diagram with two sides here, the brown material being colluvium that's deposited on top of bedrock. That's derived from some of the outcrops at higher elevation. On the left, debris flow, slope eroding. It collects huge amounts of colluvial material, fluxes them into the drainage network, takes all the trees that are in the way along with it, and fundamentally is a big volume increasing process. On the right there is what we call a blowout, which could also, again, be described as a flow slide or a liquefying rotational slide. It's failure in colluvium. It fluidizes due to the saturated nature of the material. It moves over land sort of as a wave, but it doesn't erode the slope. So it can actually move through the forest if there is forest there. If it's an open slope like the beginning example there, it's essentially a wave of liquefied soil over the land. And if you watch that video, I think the idea that water is blowing out of the slope, I mean, the visual, it looks like that. I've shown that video to geologists, and they always ask if there was a pond or something upslope that washed out to produce that effect. And no, it's simply a fluidized landslide. Kind of your detailed on the ground guide to what you would see with one of these features, and what you will see later in the talk here would be something like this. Obviously the failed area up there at the top, which typically exposes a little bit of bedrock beneath the colluvium. I've seen that in most of the examples I've personally looked at since Helene. Folded over saplings, smaller trees aren't uprooted, but the wash of material does bend them down slope. Larger trees certainly remain rooted. A lot of debris, wood debris, collects around their bases. There's also often a stacking of colluvium clasts on the upslope side of the tree, and they tend to have a big high mud line on them as that wash of material hits the tree and sort of runs up it. And then frequently, depending on the nature of the downslope topography, there will be some kind of deposit. And within that failed area, if there are trees growing there, they will ride down the slope, and they frequently end up with their root balls pointing downhill, sort of as a product of the rotational failure. And that's a detail that's not lost on people that are not geologists that observe these deposits. So what you're looking at there, again, is quite typical of this behavior. And if you watch that video, I'll stress it again, like you could not imagine that wave of material moving that fast and spreading like that came out of that scar and did not increase its volume downslope. But it absolutely did, and I can personally tell you that I've been there and seen it. Where is this place? It's up in Watauga County. The large yellow dot there is Asheville, North Carolina, along the French Broad River. You can see the lower elevations there. Watauga County is, of course, northeast of Asheville, higher elevation, a little bit different bedrock geology, though that bedrock geology is highly variable. It's all intensely metamorphosed rocks of the Appalachian Blue Ridge there. To zoom you in a bit closer, this area that's known as Sugar Grove has a lot of topography like what you see here, actually a pretty high drainage density, which is quite distinct from some of the surrounding areas where you have different lithologies. The blowout slide occurred right there at the tip of the yellow arrow. You see a road grade there. It didn't have anything to do with the road grade. It was actually down below it. If you drew an outline over its affected area, it would look something like that. My initiation point up there is probably a little bit too wide, but you're seeing that yellow outline come across the part of the house that was damaged and right off the right-hand side of a smaller structure from which that video was filmed. And overall, it would look something like that if you superimposed it onto a LiDAR image. Where that failure started out, it's in a topographic hollow. There's a little bit of a change in slope morphology that would be consistent with accumulated colluvium, or perhaps a very, very, very old slide feature there. And it's not incredibly rugged or steep topography, and that may be some of the reason, at least, why this failure did not erode the slope below it. Now, an interesting aspect of this part of Western North Carolina here in Watauga County is that it had a real big storm in August 1940, and we actually have very nice aerial photography from that event. So if I take you back to 1940, the land looks very different, heavily agricultural. And if you notice at the end of the little yellow arrow, this same area had a similar type of failure. Actually, two of them up there occur in that storm. So if I take that away, keep your eye up there where that arrow was, you can actually see the two little scars left in the landscape that were captured as these high reflectance, bright streaks of soil down the slope as a result of the 1940 event. If I took you probably a half mile or so west of this area, This is what you'd see today, what looks like pristine forested mountain slopes, a lot of tree damage from Helene there. If I take you back to 1940, that's a very different landscape. A lot fewer trees, a lot more agriculture, and more slope failures than you could ever hope to see or not hope to see, as the case may be. If you look at these closely, they are consistent with something I've seen this in California. Common in agricultural land, you get a little slide happen. It fluidizes, and if you look at that insect in the bottom left, that's east of Lompoc, California. Really, you get the fluidized material from the slide just sort of flattening the vegetation. It doesn't erode the slope at all, and that's similar to what you're seeing here in this 1940 photo. Those two slides right there have a beautiful LiDAR signature. We'll do that again. And you can see just that little scoop out of the slope right down to almost a little flat lip at its downslope edge. Looking to the left, there's probably 20 or 30 of them. Obviously, in this case, land use, I think, was having something to do with the slope behavior. But it shows you that in this part of Western North Carolina, there's probably some sort of independent variable control on what slope movements are like in extreme precipitation events. There's enough colluvium, and the colluvium is of the right character, to behave in that fashion. Take you down to Burnsville, North Carolina. This is in the Jacks Creek area. Similar behavior here to what you saw in 1940. This is all with Helene. Google Earth has newly available Helene imagery here. Looking at a nice scar up there, and with this one again, you can see that closed downslope edge of the failed area. Below it, moving towards the bottom of the screen, you see what looks like a track, what would be a scoured debris flow style track, but that is not a bare slope. That's also just vegetation being folded over by the movement of the fluidized slide material across it. And I imagine that what you're seeing here on land, in this case, there's a power line right of way. A lot of this area is still grazed, and it's grazed on very steep slopes. It obviously has a legacy over the past few decades and possibly beyond of agricultural use. I imagine what you're seeing here may be something like you would have seen in those agricultural areas during the 1940 storm to the northeast in Watauga. Stephen Fimler, our Appalachian Landslide Consultants colleague, has done a lot of field work in this area, and slopes in this part of Yancey County, sort of throughout an area here of high drainage density, they look like this extensively. These slopes did also produce scouring debris flows, but their character and appearance was overall different from what you see here. If we turn that one into LiDAR, you do see, again, a legacy of land use there, either from grazing, very old logging roads, almost like a terracing kind of effect, but mixed in with the LiDAR are scars that are very consistent with the morphology of the type of failure you saw with Helene. So in this particular case, the idea of having these localized slides that, due to the saturated nature of the moving material, immediately fluidize and just travel over land as sort of a liquefied soil wave, it's presumably something that has happened in the past. Certainly, we see considerable LiDAR evidence of that both here and throughout Western North Carolina. And the reason that we've been so interested in these features is that they appear to be sort of the calling card of these very extreme precipitation events. Frequently, you see bedrock in the failed area, colluvium above that. The failure is at or near that contact, though it does not have to be. And in the case of the Sugar Grove blowout there, that's what the bedrock looks like. I think it's highly sheared Grenville age basement, but it's, at the end of the day, thinly layered and highly intersected metamorphic rock that produces a lot of very chippy clasts there. Again, these are something that you see all over the area here. Take you up into Ashe County to a slope that does not really show any indication of human modification at any point. It probably was logged at some point, though it's extremely steep. That may not be the case. There was a blowout failure in the location as illustrated there by the yellow line. This is 2017 LiDAR. So we are not able yet to see what the LiDAR signature will be. This is what that failure looks like. The yellow lines there are describing sort of the flat lip at the downslope edge of the failed area. You can see bedrock up in the headscarp. And if you look at those trees just to the left of the yellow lines, they're of course intact. There was not scour of the slope. And you can see that organic root twig debris along with soil sort of folded around the back of those trees like I drew in my my little conceptual sketch there. This is looking back at where that previous photo was taken. And again, you can see that sort of scoop-shaped morphology that would be generally consistent with a rotational mechanism. Some of these tend to be a little more almost like translational into that lip, but they are absolutely associated with this curving failure surface. And I don't know if that curvature at the bottom edge of the failed area might be enough to alter the void geometry, with the voids being saturated to induce that sudden liquefaction. This was in a forested area. If there had been a structure below this, given the steepness of the slope above it and the size of the failure, it would have been extensively damaged just from the impact of the mass of the liquefied soil. Looking down slope, got the saplings folded over. You can see the mud lines running far up the backs of the trees. And on that slope, believe it or not, there are actually ferns. So soft stem vegetation that are still rooted in the soil, and they were just folded over. You can see those at the toe of my boot there. So the idea of this type of failure being highly mobile and liquefied, but not having an impact on the slope beneath it is how we distinguish this type of failure from what we would typically describe of as a debris flow, which is a volume increasing type of slide. Keep saying it throughout the affected area. Take you down to Henderson County now. Running roughly left to right through the middle of the screen, there's a band of outcropping bedrock. Downslope of that towards the bottom of the screen, an accumulation of colluvium. Right about that position, we had a blowout style failure. You can see the failed area there. This was actually submitted to an Appalachian Landslide Consultant client that was curious if this slide was going to have any impact well up slope, where he hopes to have a house someday. Well up slope, well above a large zone of low dip bedrock, scarp slope dipping into the slope. This is very much a shallow colluvial type of failure, but where it says intact there in the foreground, that's sort of the organic soil and root mat that was on the slope prior to this failure. I wouldn't doubt that this one uprooted some rhododendron bushes. That's the shrubby vegetation that you see there if you're not an Appalachian field person. But what was failing there, this is an adjacent slide that would have started in a similar fashion, but did erode the slope in debris flow fashion. You've got bedrock there in the foreground, and accumulated colluvium above it, in which the failure initiated. So it's a phenomenon we see throughout. First described in Pennsylvania, associated with a storm there. Very extreme precipitation, 20 plus inches of rain. Investigated that with LiDAR, and it's full of the same type of feature that we've just shown you here. When I say this was sort of a Helene-wide type of failure, you do see it everywhere. And I know a few weeks back, USGS folks talked about the huge debris flows, the most impactful debris flows in terms of the human toll in Buncombe County, in the Fairview area. We call this Craigtown. Sometimes it's called Garin Creek because of a fire station nearby. But just looking at this post-storm aerial imagery, you can very quickly see that this was the site of very long runout debris flows, a little over 2 miles from the top of the ridge down into the foreground where those networks come together. The debris flows here are obvious, but actually in this view, as you'll see momentarily, I'll point it out in a closer view, you can actually see a huge blowout style failure that occurred within these more traditional, if you will, debris flow initiation zones. And it actually ended up traveling into the drainage network and probably initiated a debris flow once it got there. So if we zoom in a little bit closer, turn that into a LiDAR view. At Appalachian Landslide Consultants, we are sort of, I guess, heavily involved in either field-supported remote sensing or remote sensing supported field work. Because the LiDAR is so critical to what we do, it's hard to know which one you can emphasize more. And certainly in our work today, they walk hand in hand. Jennifer and I have hiked the debris flows here on this range of mountains above Craigtown. And zooming in on this area, you're high up in the drainage network. You'll notice that the slope is incredibly free of road grades, evidence of human disturbance, whatever you like. And it's also sort of smooth, for lack of a better word. I mean, there's a very interesting change in grain of the landscape that's associated with lithology moving up towards these high elevations. If we throw that post-storm imagery on there, draw yellow lines around those initiation zones, paying particular attention to the one on the left, you have standard debris flow initiation zones, and the outlines here are only on those initiating areas. I'm not outlining the scour. The one on the left with the closed shape and what looks like a track below it is where a blowout style failure sent its wave of liquefied soil actually down the little channel that you can see there, and ultimately into the drainage work where debris flow style erosion began. Asked Ben Miras if I could use this image out of his talk. Right there at the end of the arrow, you can see an NDVI disturbance. You don't see one below it. And that's because that disturbance sent all of the evacuated material overland as a wave in that sort of blowout fashion. Now, once it got further downslope, it did begin to erode the channel. So what does that look like on the ground? That's what you see, and you can actually make out Jennifer up there towards the headscarp area. She's actually looking at the big macro pore, which you're going to see momentarily. But the same shape of failure, it's quite large, but you see it's closed at its downslope end. And if you look downhill from that, that's what you see. So that's literally just spinning around from where the previous image was taken. Intact trees, high mud lines, and a tremendous amount of vegetated material that was present on top of the failed area that got wrapped around those trees without any slope erosion. Sort of an interesting view here of a little sapling, and you can see those two clasts of colluvium stacked up behind it. You see that again up and right. Further downslope into the channelized area, this effect was present just at a bigger scale, and there you actually see clasts sort of buried in that mat of debris, of vegetated debris that's stuck against the tree. This is looking down into that channel area again, high mud line, and in front of me you can see trapped fine vegetation at the base of that rhododendron there. Where did all this come from? Well, you saw the blowout area, and it had this enormous macro pore. I could put my entire hand down in that. And that, as Jennifer mentioned, is something that we frequently see exposed in the headscarps of these blowout style areas. What do some of these other failures look like above Craigtown compared to that one? We'll take you up to the highest one there, right up near the summit of the ridge. An incredibly dramatic view. You would want to call it interesting, but of course, this was, I don't know, possibly maybe the worst debris flow event in recorded North Carolina history in terms of the number of fatalities associated just with this one sort of network alone. Up in those initiation zones, this actually started as a weathered rock slide there. Absolutely perfect dip slope and weathered schist, and you lost some of that weathered bedrock and just the loading of that material onto the saturated colluvium below initiated debris flow scouring there. Take it down to that one. That's the more typical failure within colluvium. You'll notice how chippy and fine all of those fragments are there. This is sort of a geologically unique mountain face. Not a lot of big boulders. Most everything you see are little plates of schist or phyllite. Massive scouring right off of the initiation zone, and down there where that prong met the sort of the main scoured track there, incredible run up or super elevation on the far bank. These were incredibly mobile debris flows, sort of in the way that you see exceptional mobility from the big blowout there. This again is a geologically unique mountain. It's right in the footwall of the Brevard Fault Zone, and most of the rock you see here are these very, very thinly layered metasediments. So in terms of looking at all of these failures, where did they occur in the landscape? It's interesting to compare them to LiDAR imagery, because just about all of them here, if you toggle them on and off, you do see the LiDAR signature of disturbance on the slope in terms of previous slope movements, particularly at top right there. There's evidence of a large weathered rock slide with a big lumpy deposit there. Close to you in the foreground, also see LiDAR signature associated with, at the very least, an exceptional accumulation of colluvium, if not a discrete process, but a very old one. Looking up towards top center, where the blowout type failure occurred and sent that wave of material all the way down the slope, hundreds and hundreds of feet over land before it got in the channel. The blowout occurred right next to what looks like the scar of a similar type of failure. And over there towards the left-hand side of the screen as well, there's an initiation zone that's in close proximity to some scarring on the slope. So in this particular example, it's hard to know if you would call it reactivation, but it appears it was not this slope's first time to experience slope movement. Now, we don't see relic scouring on the scale that developed, and it begs the question of timing and sort of how far back into geologic history you're looking here. But suffice it to say, thinking about what is present on the slope and what moved this time around, and looking forward in terms of thinking about what could move in future events, it's this combination of LiDAR evaluation with field verification that is what we do at Appalachian Landslide Consultants, and what we have been doing for the past several years in terms of landslide inventorying with the counties for the North Carolina Geological Survey. Sometimes you have to take that sort of to the next level. The overlays that I'm showing here, particularly the aerial imagery there, I'm actually getting those as exported image files from the Buncombe County GIS server, and then I'm locating them into Google Earth here just to have the interface that we're looking at. To take you somewhere close by to what we've just been looking at, when I say close by, really close by, you're actually just on the north side of the mountain. So if we went back to that image and you went straight up north off the very top of the screen there, you'd be looking at this area. This is a neighborhood that drains to the Swananoa River. Keep saying this is a geologically unique mountain here. Essentially, it's called the Swananoa Mountains. It's sort of an extensive ridge. It's basically like a hogback type of a feature, almost a valley and ridge type of topography, where there's a very resistant band of metagraywackies that hold up the ridge. Debris flow processes were very different on this side of the mountain, despite being just over the ridge. At the end of the arrow there's actually a pretty significant debris flow IZ that you just can't see with the aerial topography. You can very faintly make one out just right of center of the screen. We'll bring those outlines on again. But the one that comes down from the tip of the arrow, it's almost invisible. There was some loss of vegetation associated with it, though less than you see, of course, with the scouring on the south side of the ridge. And actually between those two prongs there's probably 6 or 8 initiation zones that just did not proceed to long run out debris flows that made a substantial impact on the slope. I hiked all this a couple of weeks after Helene at the request of a property owner whose house is actually right down there where those two prongs meet. For whatever reason, and I personally would attribute it to bedrock geology, slope processes on this side of the Swananoa Mountains were quite distinct from what you saw on the south face. How much of that has to do with the precipitation gradient, I don't know, but it's not to say that the slope you're looking at right now is not absolutely full of slope movements, which it is. They just evolved very, very differently from what you had on the other side. And if you look at a LiDAR image of that slope, first of all, there's an incredible amount of road cut and whatever else. The debris flow there that you see at right, so the right hand of those sort of Y-shaped joining tracks, that goes right up to an old logging road there. And yes, that is most certainly where that one initiated. The one at the left initiated on a natural slope. It's a colluvial slope, but just the grain of the topography here you see with that meta-gray wacky bedrock is quite distinct from what you have on the south slope, where it's dominated by those schists or phyllites, which are actually locally graphitic. Right in the top left of the screen, in fact, you can see that sort of cliff band, if you will, that is basically the cap rock holding up the ridge there. Exactly how the different lithology would affect debris flow behavior, couldn't tell you for sure, but I've got you right now up in that initiation zone that you just really can't see with aerial imagery. You see bedrock exposed in the foreground. Excuse the poor quality. I actually took a video for the property owner, and this is just screenshots of it. But as you look down slope, if you take a look at some of those small boulders, big colluvial fragments there that you see in the bottom left, they're not the thin chips and plates. They are very much larger, more prismatic rock fragments. You see them again there. The debris flow track and deposit on this side of the mountain in this particular location, it is just dominated by big coarse clasts. And I think we go back to the LiDAR. If you look just below center of the screen, you almost see that lumpy bouldery character where that material has accumulated from outcrop sources upslope. And I don't know how the folks living in that house had two substantial debris flows merge above their home and give it sort of a glancing glow. There's a lot of homes actually just off the bottom of the screen here. The flow just ran out of steam very, very quickly. As soon as there was any reduction in gradient, it slowed to the point that it continued to move fines and larger rocks floated by the liquefied soil, but it lost the velocity and it lost the runout distance that you see on the south side of the slope. This one was interesting to visit because it's literally just over the mountain from what again could be considered the worst debris flow event of the entire storm. The evidence of runoff related minor flooding, you're high up in the drainage network here, but there's not evidence in terms of the channel appearance or in terms of the number of slope failures, again, of which there are plenty here, that would give you any indication that for some reason you just didn't get the intensity of rainfall here. It's very much like the distinction in bedrock geology, the distinction in the colluvium present to be mobilized was enough to sort of alter the debris flow behavior. But that's of course a very slippery slope to walk, because you wouldn't want to go around saying, well, there will be debris flows here, but because of this bedrock geology, they're not quite as likely to be long run out or something like that. So take that with a grain of salt. But like so much of the Appalachian landscape, which is so strongly controlled by bedrock character, why does this mountain look like this? Why is it this tall? Whatever. Just about everywhere throughout southern Appalachia, the answer to that question is bedrock distinctions. And I wouldn't be at all surprised if you could see systematic variation in landslide and debris flow behavior that is also a product of those distinctions in bedrock lithology. So getting towards the end here, and I want to be sure to leave a little bit of time for us to do some questions. I'll take you just north across the Swannanoa River, which of course, if you followed the Helene event, was certainly one of the ground zeros, if you will. The scale of flooding on the Swannanoa River was something that has not, of course, been observed in recorded history. If you go just north of the Swannanoa River very quickly, the landscape rises up into a steep prong of the Blue Ridge that's actually sort of a southwest continuation there of the Black Mountains. Geologically distinct from what you see down there in the Craigtown area that's right above the Brevard Zone. And this was a landscape, again, that was host to quite a few debris flows. The first one I'll show here is one that was the direct result of a modified slope, actually of an old road embankment on what certainly appears to be a disused road. So there's your LiDAR view. Of course, in the foreground, a tremendous number of house pads. This is a densely developed and populated area right at the base of this steep slope, which exposes a lot of bedrock and has quite a bit of colluvium sitting rather precariously on top of what are often very nicely sloping bedrock surfaces down beneath it. We'll fade in some of this great Buncombe County GIS imagery, which was taken sometime when the leaves were still on the trees after the storm, but the resolution of it's really exceptional, and it does fit very nicely in terms of an overlay here. If you look down at the bottom of the screen, you can see that debris flow track coming into contact with quite a few houses, and we'll trace the outline of that debris flow, and then we'll fade that imagery away. And you got that IZ sitting right where you think it might be on an embankment on that disused road. And as portrayed here, it actually did come down slope, encounter sort of a flatter area of the slope, and then make kind of a turn and continue off where it came into direct contact with a number of structures. I believe this one led to 2 fatalities. And my understanding from Dave Cordy with NCGS is that it essentially stacked, it hit structures and sort of stacked them on top of one another. If you go up to where this thing initiated, looking just at the initiation zone, you'd see something like that, and we'll toggle that on and off. You'll note that there's a good bit of embankment on the downslope edge of the road there. It's like they wanted to build that up through a little bit of a topographic hollow there, just to be able to support the road. So there's cut, but there's also introduced material to try to support that road, which is effectively a surcharge on the natural slope there. What does it look like in person? That's a photo from it from just a few weeks ago. The yellow lines there are used to point you out to the surface of the road grade there. So about half of the road grade failed away. This is an interesting example because it's an embankment right above a cut slope on the road below it that you see right at the edge of the image there. Whether this started on the embankment or started on the cut slope and quickly retrogressed up to the embankment, we don't know that. But for sure, the modification of the slope here was absolutely the trigger for the failure in this particular spot. If you look at the failed edge of the road grade, you can see quite a few sort of platy clasts sticking out of there. Looking closer at that, like so many roads here, I presume they were taking either sourced fill material from somewhere close by on the mountain, or maybe they're even using the material that they cut off of the slope and just depositing that there to build up the embankment. This was not an engineered road embankment by any stretch of the imagination. And with this storm, unfortunately, it produced a very catastrophic outcome. Moving just to the east of that location, this is one I think that Ben Meares talked about as well. It's certainly one of the most obvious, for lack of a better word, debris flows from the post-storm aerial imagery. This came down on a retreat center called Shepherd of the Hills. We'll outline it there and take it back to LiDAR. And you can see that this one also initiated on a colluvial slope with plenty of bedrock around it. In this case, it's a natural slope. There's no modification up there. And this one followed a very well-worn path down slope, a channel that has probably carried plenty of debris flows in the past and built up that flat, broad deposit area where this one also deposited its material. Where did this one come from? That's generally the outline of the initiation zone there, between bedrock outcrops, sort of the inspiration for my debris flow in the conceptual sketch from the beginning of the talk there, where it's just a localized area of thin colluvial storage sitting on a bedrock surface. not terribly large. That's what it looks like in person. That's Jennifer Bauer noting the point there for our mapping purposes. And to the right of the image, you can actually see that thin colluvial veneer that failed off of that bedrock surface. Excuse me, long days in the field here before the seminar. Colluvial thickness here just 2 or 3 feet. If you look downslope, there's already mud lines on the trees straight off the bottom of the initiation zone, so it immediately fluidized, and it ended up depositing down there in the distance. So this is a useful visual in terms of seeing how a fairly limited volume of material starting out can make its way down slope, and as you'll see momentarily, produce an absolutely enormous deposit. A big question here, of course, is why did it fail right there? We don't know the answer to that question. We probably never will, but any failure from anything that you see from that 55-foot label to the left is going to follow the track that this debris flow followed. And if you look at the structures pre-storm versus post-storm, there are a lot of areas here in harm's way. No one was killed or seriously injured with this particular debris flow. That's nothing but luck, because again, it absolutely eliminated several structures. And the idea that this location was one that was heavily used because, among other things, it was a nice flat spot at the bottom of the mountain. Folks don't normally think about why that area is flat like that, and it is, of course, just the combined effects of processes like this occurring at interval throughout recent geologic history. Absolutely enormous deposit, about 200 feet wide, 1,800 feet long. That's basically from the mouth of the little channel up there. But to go from that initial failure scar with just a wafer thin layer of colluvium on it to produce a deposit that big, the amount of material that was scoured out of the channel in this example is, at its scale, just the effect of the visual. It's something like you would have seen in the Craigtown example to the south. So wrapping up here to give us again enough time for questions. Where do we go from here? That was the end of my title. So we looked at where they started. We looked at where these debris flows and blowouts go. What do you do next? I mean, how do you make this useful, actionable information? And that's a tough question to answer. The majority of slope failures that I have personally visited, I think that ALC has visited, they initiated in areas that modeling we use and modeling that the NCGS uses would predict slope failures to initiate, and the Craigtown examples are really not an exception to that. What we don't understand, and what has proven much more difficult to constrain without examples like this, is what runouts are going to look like, what runout links are going to look like. How might those be impacted by the amount of precipitation? The Craigtown example here, by the time you get to the bottom of the hill, you're getting into you're into higher order streams, like you're farther up in the drainage network, and certainly the amount of water moving there is going to be contributing to the behavior of the flowing material. But the runout links here, again, from the top of the ridge towards the top of the screen to the junction there in the foreground, it's if I'm not mistaken, it's over 2 miles. And how was this behaving when it got to the bottom of the screen? I don't know. It was probably in the hyper concentrated flow realm at that point, perhaps. But the prong there on the left scoured through the little gorge there, sort of in debris flow fashion. Trying to understand how these things are going to behave on the downslope end it's to me an important question, and it's one that hopefully we'll be able to make some headway on, because if for no other reason, we have a lot of examples now that are going to be useful to inform modeling. But kind of a final thought, and not necessarily the happiest thought to end on. This is sort of the specific Craigtown community. The white roofed building on the right there is the Garin Creek Fire Station that gives its name to this area, though it's not on Garin Creek. Garin Creek is actually, believe it or not, across the Eastern Continental Divide to the west of here. Garin Creek is in the French Broad Basin. The small stream that you see flowing from top to bottom in the image here is the headwaters of a creek called Flat Creek that's part of the Rocky Broad River. So this actually drained to Bat Cave and Chimney Rock, and in some respects, you could say that the debris flows here coming off of the Swannanoa Mountains down to Craigtown were, in a sense, the beginning, if you will, of the Chimney Rock flood, at least in a topographic sense. The folks living in the houses down there, particularly the ones that are near the center of the screen, if you talk to them, the way they visualized hazard living here was based on the behavior of flowing water in the little stream, which they call Craig Branch at this point. I don't think it's even called Flat Creek here yet. How high will Craig Branch get? Well, the highest we've ever seen Craig Branch is, well below the houses, well below the roads. There's absolutely no way that that's going to impact my home here. And actually, they said that before the debris flows came through, Craig Branch was as high as they'd ever seen it, which was still certainly not flooding anybody's home. So their perspective on dangerous behavior of the landscape was entirely from a water and a channel point of view. And that is the after effect of the debris flows. There were several waves, 3 or 4 waves came through here. You can sort of put all that together on your own just from looking at the image. That's about 300 feet wide. So just at the very least, communicating to people in places like this, and it's bad that this has to become an example in this way, but hopefully going forward within the region, folks will be interested in accessing this information and will be able to get it to them, and will also be able to have a better understanding of what slopes are capable of producing in the sense of what you see here. Because just based on topography alone, if you had asked me before the storm, where will you see the most damaging or the most deadly debris flow activity, I would not have picked this location. I would have said McDowell County, which of course was very severely impacted, maybe somewhere right on the escarpment. I don't think this would have been my answer. So hopefully we can take this information, take it forward, and be better prepared for the next one. Hopefully it's not a Helene scale, but absolutely within our careers we will see debris flow producing storms here in the Appalachians again. So hopefully we can be even more ready for the next one than we were this time. So that's all I got, and we'll take some questions now.